because of time we had to save this for today, but this is part 2 of day 2 of 4-3. Kind of a mouthful there. But a point of inflection is a place where basically, as it says right here, or it doesn't say right there. Anyways, it is a place where it changes from concave up to down. Okay, so points where the original, very important to know there, changes from concave up to concave down, or vice versa, meaning it can change from concave down to concave up. Okay? And that makes sense. Again, the most common one is if you have your x to the third graph. Right there, it changes from concave down to concave up, and that's a point of inflection. That's probably the best example that we can use for a point of inflection. So here it says to determine all points of inflection, so I need to know where does it change from concave up to concave down. So very similar to what we did yesterday, but the derivative is going to be a little bit easier on this one. And the first derivative is 4x to the third minus 12x squared, so no big deal there. But again, if we're talking about concavity, we're going to get that second derivative, because that's what the second derivative test tells us, concave up or down. Remember, first derivative tells you increasing, decreasing, where second derivative tells you concave up and down. This one's quite simple, 12x squared minus 24x. And if we take a look at 12x squared minus 24x, that's not undefined ever, so we don't have to worry about that. And then, is it ever 0? Well, I think there are probably plenty of times it will be 0. You could do this many different ways. I would probably factor out the 12x if I was doing it, and get x minus 2 in here then. And remember, if you set it equal to 0 like this, you can set each piece equal to 0. So 12x set equal to 0 gives me that x could equal 0. And then also this other one, x could equal 2. So these are potential places that it could change concavity. Not change from increasing to decreasing, that's first derivative, but where it could change concavity. And so we're going to want to set up some intervals. And if you look back at the original, there's no places to worry about there. There's no asymptotes or anything like that. So we can actually just say negative infinity to the first one we would come across, which would be 0, and then 0 to 2, and then 2 to infinity. Now for testing concavity, we're going to want to test a point in that interval, because from negative infinity to 0, it either is concave up or down. It can't change, all right? And so maybe you wanted to try, I don't know, negative 10 or something like that. And so a very easy place to substitute that in is into your second derivative. Either version here, it doesn't matter. But I would say maybe go to the top one here in case you made an algebra mistake or something. So you put negative 10 right in there and you square it. Well, that's positive. And then I put a negative in the other x. It's a negative times a negative. So they're both positive. So it ends up being very much positive, which means this interval here is concave up. And from 0 to 2, you pick some value. 1 is probably the obvious choice. You put in 1 back where we did before. You square it. It's 1 times 12 is 12. Minus 24 is what it ends up being. And so that is a negative value. So this one is concave down. And from 2 to infinity, you pick some value, maybe 10 or something like that, to kind of make it obvious. 10 squared is 100 times 12 is 120. Basically, minus, or excuse me, is 1200 minus 240, excuse me, sorry about that, is it ends up being positive, which makes this one concave up that whole time. Got a little ahead of myself there. And so if we're looking for points of inflection or places it can change from concave up or down, well, does it change at 0? It was a potential place. Well, it changes from up to down, so 0 is a point of inflection. And we'll abbreviate that POI, point of inflection. And if I ask for, let's say points of inflection, so we better get the y value. And to get the y value, we will substitute it back into the original. So 0 there, and so it's 0, 0. So how about 2? 2 is another potential place. It changes from down to up, so it actually is. So another one is 2. So you put 2 in there. 2 to the fourth, if we're putting it back into the original, is what, 32? 2, so minus, nope. 2 to the fourth, 16, excuse me, minus 32, so negative 16. So 2, negative 16 are places it's going to change. So right there, and unfortunately way off my graph somewhere down there. And to give you an idea of what it looks like, you can always graph it on your graphing calculators, but right there it does take a change. And actually this kind of keeps coming down like this, and then it switches over back to concave up like that. Sorry, that would be another point of inflection down there. But here it kind of changes over from being concave down, because that's what it's supposed to do from 0 to 2, back to concave up from 2 to infinity. And so all the rest of the way it's concave up. And here it's also concave up. And that's about what the graph looks like. Again, you could take a look at that on your graphing calculator. That is just a sketch, but it does show you the concave up versus concave down, and it shows you the points of inflection. Okay. If there's any questions with that, I can definitely field those when time permits. Example 3, it does say to locate relative extrema, which you could have done that just using the first derivative. And if you did that, that's fine. You know, we can kind of talk about that when I return. But I did want you to kind of use the second derivative, and I'll kind of show you how you could do that. So the first derivative, that's where you're going to find extrema, is negative 15 x to the fourth plus 15x squared. And that's never undefined, so you don't have to worry about it. And then you would set that equal to 0 to find out potential extrema. And I would probably factor out the negative 15x squared. You don't have to do it this way, but it is a way that works. Then you get x squared minus 1. And again, you set each one of those equal to 0, so you get x equals 0. And if you set x squared minus 1 equal to 0, you get x equals positive and negative 1, because you do have to take that square root. Now, if you went and found intervals and all that stuff, that's fine. You could have done that. But what I would like to do today is show you how you could have potentially used the second derivative if you wanted to. You don't have to. But seeing this second derivative is fairly easy to take. It might not be a bad idea, because you get negative 60x to the third plus 30x. And what we're going to do is we are going to find out, we want to figure out well, we don't really have to set this equal to 0. If you did, you would have gotten that x equals 0 and x equals positive and negative square root of 2 over 2. And you could have found where it's concave up and down if you wanted to. But that's not what we were going for here. What I really wanted you to use, and sorry for being gone, but is that let's actually go ahead and let's put all of these values into the second derivative and find out what happens. We haven't done that yet. And what it's going to tell me is it concave up or down at that particular extrema? And so what we can do is let's go ahead, let's put in, 1, let's put in negative 1, and let's put in 0. And so if we put 1 into the second derivative, we find out that, so you put 1 basically right here and right there. And so 1 to the third is obviously 1, so that's negative 60 plus 30, negative 60 plus 30, yep, is what? Negative 30? Okay, and then you plug in negative 1 to the third. It's negative 1 times negative 60 is 60, so 60 minus 30, you get a positive 30. Is that right? Something doesn't seem right, but we'll keep going. You put 0 in and you get 0. Well, f prime, double prime of 1. So that means at 1, it is, at a value of 1, it is concave down. Okay? And at a value of negative 1, it gave us a positive value, which would mean it was concave up. And at 0, it gave us 0, so that's neither positive or negative, and so we would have to go about finding that another way if we get anything for 0. Most times you will not, but you would have to go about other methods for checking that one. And so, again, what we did is we put a value in and we got that it's negative. Remember, negative means concave down, which would mean 1 would be sitting right there, making it a max. And it came out a positive here, which means smiley face. And so at negative 1, there should be a min. And so what we could do is quite easily take a look at this particular sketch and see what happens. Because you did find the extrema then. At 1 would be a relative max, and at -1 it'd be a relative min. And let's take a look at the graph and find out what happens. And let's see, is this the graph? Yes it is. So here it is right here at -1, right there. And here's +1, and here's 0. So 0, it's kind of doing one of these. And so that would tell us that at 0, it's still a critical number, but it is a point of inflection. And that at -1, we had a relative min, and at +1, we had a relative max. And so let's see if that matches what we said. I think it does. You might want to get this sketch in there. It's kind of that, kind of looks like a cubic graph, but it is kind of upside down, which makes sense. Okay. So let's see if that matches what we had. We had 1 being a relative max and -1 being a relative min. And so that's one way that if you don't want to do all those intervals, it's another way to get there. And hopefully, if you did intervals, you got the same thing. Okay. Again, if there's any questions, I can field those when I return.